Our project focuses on fluid and rigid body motion. A rigid body is a solid body in which deformations are essentially zero. The distance between any two given points on a rigid body remain constant. For problems like the one we tried to solve, the fluid acts as a rigid body. So these problems can be considered fluid statics problems. Our project was modeled off of example 2.19 in the third edition of the De Nevers text, which aims to find the difference in the height of the fluid at the center of a fluid-filled cylinder versus the height at the wall. For the derivation, we consider the fact that there is pressure in both the z direction and in the radial direction. With rigid body motion problems, we sum the acceleration of the fluid in the a direction with the acceleration of gravity in the equation for pressure. In our problem, with the acceleration of the fluid being in the radial direction, the cosine of the angle theta equals 0, and so the gravity term drops out. Integrating with respect to r yields the bolded equation, and then substituting rho g delta z for pressure and rearranging yields the final equation for change in height.
Using the derivation from the previous slide, we determined that we should fill 3 different beakers with different diameters of 6 centimeters of water. With these differing beakers, we determined that we could put them onto a magnetic stir plate where we inserted a magnetic stir bar to create a vortex.
The vortex in our experiment creates an angular velocity gradient in the radial direction. This is due to the no-slip condition at the wall, so the angular velocity goes from 0 at the wall to a maximum at the center.
With a constant diameter and varying velocity, the images below show the results using a 250 milliliter beaker with angular velocities ranging from 0 to 500 revolutions per minute at 100 RPM increments. As you can see, the parabola height increased with each increase in velocity. Experimental data showed an increase in delta z, but at a less pronounced rate as the theoretical curve. The same experiment was repeated for 2 more cases using 1,000 and 2,000 milliliter beakers. These resulted in even greater deviations from the expected curve. Looking to the second part of the experiment, where velocity was constant and diameter was varied, the theoretical calculations revealed that delta z had an approximately linear relationship with radius at constant velocity. As you can see by the plot at 500 RPMs, this linear relationship was not depicted by the results, as radial increase showed to have little effect on delta z. Calculations were made for all other angular velocities, yielding similar trends. We identified the main source of error for both parts of the experiment to be the use of a magnetic stir bar, which produced a vortex as opposed to the expected parabola, seen in the photo below. This was observed using a petri dish inoculating turntable, which would rotate the beaker when a tangential force was applied. Notice you can see the smooth parabolic shape of the water. Ideally, a digital turntable with a range of angular velocities would be used to rotate the beaker as a whole in order to induce the effects of centripetal acceleration. This would more accurately depict the increase in free surface height of the water along the wall. However, without a digital turntable at our disposal, the best method to model accelerated rigid body motion was the stir bar, which did not rotate the beaker itself, rather just circulated the water within the beaker, thus creating a vortex.